Hi everyone, and welcome to my YouTube channel, and welcome to another episode of Visuals with Maan. In this episode, we're going to explore a stunning narrative from the history of mathematics. When we immerse ourselves in the historical timeline of mathematics, we notice something striking. Following the obvious intuition of the majority can often lead to a major breakdown in understanding. This inspires us to question the established conclusions and discourses. To consider this counterintuitive question, can a curve that is completely smooth actually be completely non-smooth? So what if a function is continuous everywhere but has no tangent anywhere? At the end of this video lesson, together with the worksheet provided in the description below, you'll be able to achieve the following learning objectives. So please pause the video and take a look at each one carefully. And I hope that this video sparks your curiosity and interest, and it would be lovely and wonderful to have you stay until the end of this video lesson. The figure featured in this video lesson is Karl Weierstrass and his 19th century contribution to mathematical analysis. His work marked a major paradigm shift. Continuity does not imply differentiability. In this video lesson, we will explore three narratives about his life and work. And a more detailed discussion can be found in the worksheet provided in the description below. Karl Weierstrass was a school teacher before becoming a pioneer of modern analysis. He endured difficult years with limited access to colleagues, libraries, and scientific exchanges. Those miserable years, he had neither a colleague nor access to mathematical library. Exchanges of scientific letters was a luxury. In the historical narrative of mathematics, we know that certain assumptions can be deeply dangerous, as seen in the early discussions of the irrationality of square root of 2. Yet, mathematical thought has continued to progress, and mathematicians have gradually embraced counterintuitive ideas. Before the work of Karl Weierstrass, many 19th century mathematicians believed that every continuous function must be smooth and differentiable almost everywhere. This assumption reflects the prevailing methodology of the time. Calculus was still very much rooted in visual geometry rather than in rigorous algebraic foundations. Karl Weierstrass' work challenged that belief and reshaped the standards of mathematical reasoning itself. Karl Weierstrass deserved recognition for boldly replacing intuition with rigor in mathematics. By the way, the epsilon delta framework is beyond the scope of this video, as mathematical analysis will be explored separately. One of the beautiful aspects of the history of mathematics is that each topic offers only a glimpse, just enough to sense the depth and landscape of the discipline. In this way, we will appreciate the nature of mathematical thinking and rigor behind it. Weierstrass' algebraic rigor can be experienced through formal study and mathematical analysis textbooks and courses. Again, continuity does not imply differentiability. For now, we will explore this idea through three learning activities. Alright, so please take a moment to see what this exploration is all about. When encountering a classical Weierstrass function, please do not just stare at the formula, experience it, okay? So in this activity, we're going to combine modern technology with classical mathematical practice. GeoGebra will help us visualize the graph, and a manual X and Y tabulation will help us experience the calculation, and a four-term approximation will be used to make the calculations practical. So GeoGebra draws the curve, but constructing the table by hand will allow us to witness and experience the numerical behavior of the function unfold before our eyes. And yes, GeoGebra can create the table, but there is something magical and valuable in experiencing the process ourselves, right? So please check out the accompanying YouTube short link in the description below. So go old school experience the math, and marvel at the beauty of the function that have changed and shaped the history of analysis. At this point, I will show and provide a demo on how to make our visualizations in GeoGebra and in Python. Okay, to everyone, this is the finite four-term approximation here. Okay, so I will link in the description below this GeoGebra applet here. Start with a simple triangle function, and as we increase the n, we notice that even if it's continuous, it's not smooth, okay, and it's not differentiable anywhere. And now we are going to run the Python script. Alright, so we now have the Python app here. Okay, so again, we start at a very simple triangle function. It's very smooth, and there can be tangent everywhere here, but as we increase the n, we notice that there are some oscillations, okay, and there are rough edges. There's roughness in the continuous function. Alright, so in this case, there is no tangent anywhere. Alright, so that's how we can visualize and experience the Weierstrass function. We are at the end of our video lesson. Please pause the video and take time to go through the concluding points. So again, we are called to be catalysts for discovery. What was once seen as mathematical pathology now underpins measure theory and fractal geometry, showing how counterexamples deepen our understanding of the universe. Alright, so thank you so much for watching until the end of this video. Until next time, I'll see you in the next episode of Visuals with Maan. Bye for now.